we're going to talk about my favorite hormone, insulin. Well, actually, we're going to talk about insulin and glucagon, but we're going to start with insulin, right? So we're essentially going to be talking about a gland named pancreas. Anatomically, it is posterior to stomach, blah, blah, blah. It is one of the unique glands that is both endocrine and exocrine. We're going to learn the exocrine role of pancreas in the digestive system unit. So far, we're going to focus on endocrine. So out of 4 types of cells that comprise pancreas, I'd be honest, I'm going to be focusing on the first 2, alpha cells and beta cells. There are alpha, beta, delta, and PP cells. So alpha cells produce glucagon. Beta cells produce insulin. And delta cells, they produce somatostatin. So basically growth hormone and inhibiting hormone. That's the last time we're going to talk about delta cells. That's it. Like we're not going to be focusing on these ones anymore. And we're going to focus on these 2. Right? We're clear. So first, let's discuss the regulation. And regulation is actually very, very simple. I'm going to lay them next to each other because essentially the effects are diametrically opposite. So we're going to start with glucagon, and the stimulus for glucagon release is low blood glucose. Does that make sense? That results in the release of glucagon from the alpha cells. Am I clear? Good? Next to it, I'm going to position insulin. So we have increased blood glucose, which results in the release of insulin. Now, it's entirely up to you. Let's make it interactive. Which one? It doesn't matter. Which hormone do you want to start with? Glucagon or insulin? Your choice. Then the mechanics of the response. Which one do you want to start with? Sure. Let's do insulin first. So, insulin is released into the blood. And what is the overall effect of insulin? Huh? Lowers blood sugar. The question is, how? So I'm going to give you a task and we're going to discuss how we can, perform it. So you have elevated levels of glucose in the blood. You need to lower it. How? The answer lies not in the endocrine system, it lies in common sense, just general understanding. What do we need glucose for? Energy for what? It's not a hard question. For what? Everything. And that everything, all these processes that we need energy for, in which, wink wink, elementary building block of the body, these processes happen. How do we call elementary building blocks of the human body? Human body is composed of what? Elementary building blocks of life. Come on, people. What are we made of? I have it on my freaking t-shirt. Cells. Okay, so all the processes that are in the cell, right, they require energy. Correct? And energy source, primary energy source is carbs, glucose. Where do we need to deliver glucose then? It's of no use in the blood. Where does it have to go?
To the cells.
Bingo, into the cells. So, first outcome is increased glucose uptake. Does that make sense to you? We're good? glucose goes into the cell. Now, I'm going to appeal to your previous biology knowledge. Please don't be shy. Like this glucose that's in the cell, is it just like provides energy directly, or what happens to it? Like, what is the main molecule that is produced in that powerhouse? ATP. So glucose is used to make ATP. Does that make sense? It happens in the process of cellular respiration or fermentation. These processes have one step in common. It's glycolysis. So insulin will increase the utilization of glucose. Glycolysis literally means the breakdown of glucose. Does that make sense? Now let's say glucose keeps coming. So it satisfies all your needs in terms of glycolysis, but you have some extra. If you have some extra of, let's say, food, what do you do with it? Bingo. So you're going to store it in two forms. One form is glycogen, okay? Another form is, if you eat a lot of sweets, 5 minutes on the lips, 5 years on the hips, in the form of fat, right? So two ways, glucagon and fat. So increased, not glucagon, glycogen, I'm sorry. Increased glycogenesis. So glycogenesis refers to increased storage of glycogen and increased lipogenesis. Does that make sense? So you're essentially increasing, question? Can you just, all right, so we got this, right? These are all the processes that are stimulated by insulin. We clear? So we take glucose in, we break it down for energy, for ATP, we store the extras, and we store the extras. Am I clear? Good? Now let's talk about glucagon. So you have low blood glucose. Where can you take it from? Glucose, where can you get it from? Now you need to do an opposite. Now you need to increase the glucose in the blood. What can be a source of glucose? Okay, you can break down fat, right? It's not direct, but yeah, it's a good idea. You can break down fat, you can increase lipolysis. What else can you break down? Can you break down glycogen? So, increased glycogenolysis. We're good? Can you break down, can you make glucose from scratch? Yeah, sure, why not? So we call this process gluconeogenesis. Does that make sense? Gluconeogenesis. Glucose, new, making. Does that make sense? So these are the terms that I will be using in the exam, and these are the terms that you have to understand. Are you with me on this one? It's not like I'm not trying to scare you, obviously. I'm just telling you that for the exam, I can ask you a question: which of the following processes is increased by insulin or stimulated by insulin? And I will give you a list. Let's say I'm telling you, insulin stimulates lipolysis, glycogenolysis, gluconeogenesis, lipogenesis. You look at this and say, it stimulates lipogenesis only. But if you come to me and ask, what does this word mean? I won't be able to tell you. I'm telling you to know the vocabulary. Does that make sense? Good? So that's basically the mechanics. Couple more things that I wanted to throw on top of that is the mechanism of signaling. Well, glucagon is water-soluble hormone that works through the classic second messenger system, okay? Actually, via two of them. There are two different second messenger systems that glucagon can work through. It's all via G-protein coupled receptors. Now, insulin works through the tyrosine kinase receptor. Okay, we're good so far? Tyrosine kinase receptor. One of the three pathways that we learned last week, as one of them was tyrosine kinase. Now, I can't help it, but I love the mechanism, how glucose stimulates the release of insulin. And we're gonna look at it now. So imagine that this is your beta cell. Okay, does that make sense? Good. So every cell in the human body has some baseline level of expression of glucose transporters, GLUT. GLUT stands for glucose transporter. It's basically a channel of sorts, okay? Make sense so far? So imagine that you have elevated blood glucose. You ate something sweet. That make sense? So glucose levels in the extracellular fluid outside of the cell, they go up. And they become higher than the glucose levels in the cell. Are you following me so far? So what's going to happen to glucose? It's going to do what? If the levels outside are higher than the inside, glucose will be D word. Nobody's going to continue that? Diffusing into the cell. Okay? So, Emma mentioned the role of glucose in the cell. It is the source of what? Energy. But the energy in the cell is transferred from one part of the cell to another in the form of which molecule? ATP. So if you have more glucose in the cell, it automatically means that the levels of ATP, what happens to them? Huh? They're going to go up or down. More glucose, more ATP. Turns out ATP isn't only an energy molecule, it is also a pretty powerful ligand. That makes sense? Which opens and closes ligand-gated channels. So you have a potassium channel, which normally, now listen up, normally this potassium channel will allow potassium to escape from the cell. Does that make sense? Are you following me? But ATP will close this channel. Now, with the potassium channel closed, potassium cannot get out of the cell. Does that make sense so far? And it stays in the cell. What is the charge of potassium? The reason why I know that a lot of questions that I ask, answers are written right there, but when you say it, it facilitates your learning process. So, when positively charged ions become trapped within the cell, what happens to the charge within the cell? Cell becomes more positive, right? Anyone remembers what we call a state when cell becomes more positive? It's a word polarization with some prefix. Cell becomes more positive, cell is depolarized. So cell becomes depolarized. Does that make sense? and that depolarization change in the membrane potential opens, I'm going to do this circle as the sign of opening, opens calcium channels. Okay? Does that make sense? I'm going to go over this one more time, no worries. It opens calcium channels. Okay? Julia, feel free to ask what I've written because I know I'm not the best writer in the world. Okay, so opens calcium channels. Anyone remembers the concentrations of ions across the membrane? Calcium, okay, concentration of calcium. Is it higher outside of the cell or inside? Outside. I ask my AP1 students to memorize 4 ions. Calcium, sodium, potassium, chloride. Calcium, sodium, chloride are higher outside. Potassium is higher inside. So calcium concentration is higher on the outside. And which direction calcium will go then? And calcium diffuses into the cell. Now let's leap towards AP1. If you will try to recall a synaptic transmission of, signal between the neurons, so between the neuron and a muscle cell, you may remember something about calcium. On presynaptic neuron, when calcium gets into the cell, this results in the release of neurotransmitter. Does that make sense? Here, calcium enters into the cell and stimulates the release of insulin from the vesicles. So to some extent, this is kind of akin to the release of neurotransmitter. Does that make sense to you? So going over this stuff again. Elevated glucose levels result in diffusion of glucose into the cell. Increased glucose means increased ATP. Increased ATP closes potassium channels. Potassium gets stuck in a cell, depolarizes it. Does that make sense so far? Depolarization opens calcium channels. Calcium diffuses into the cell, releasing insulin out of it. Are we clear? So, very, very simple question. When do you produce insulin? After what? After a meal, yeah. Right now I'm making insulin. Okay? And one other, so insulin actually, when we talk about insulin, just kind of illustrate, when we talk about insulin as a hormone that decreases your blood glucose, it's technically wrong. I mean, it does it, but the goal of insulin is not to decrease your blood glucose. If you think about it, think about the whole digestive process. So I ate something, right? This something got digested in my GI tract, and nutrients, glucose, amino acids, and fats got absorbed into the bloodstream. Does that make sense? They are of no use in the bloodstream. I need them in the cells. So insulin will stimulate glucose uptake. It will stimulate amino acid uptake into the cells, right? And it will indirectly stimulate lipogenesis, deposition of fat, and utilization of fat as the energy source. Does that make sense? So basically insulin delivers energy-bearing molecules and building blocks of proteins into the cells. Is that clear? Now, sounds very basic, I know. So if you will ask a professional bodybuilder, not for the record, if they are clean, I can guarantee you the answer will be, no, we're not. I had a student who did a professional bodybuilding, like not just go into the gym, doing training, like bodybuilding competitions and stuff. And he said that the idea that, they all use testosterone is, not really, they don't. They use various anabolic steroids, but they work with endocrinologists because they also need insulin. They use insulin, very carefully to increase the uptake of amino acids and glucose and fat into the cells to stimulate the growth of muscle. Does that make sense? And as a matter of fact, if you will, I have an example I think in my lecture notes. If you will take rats and cut off pancreas and cut off the anterior pituitary, so rats have no growth hormone and no insulin, those rats obviously won't grow. Does that make sense? If you will give them just growth hormone, they still won't grow. If you give them just insulin, they won't grow. But if you combine those two and give them exogenous insulin and growth hormone, rats will grow like normal. So you need both of them to properly grow. Am I clear? Now, let's talk about the elephant in the room, diabetes. There are two types, type 1 and type 2. So in type 1, what's the problem in type 1? No functional beta cells. Now, look, I make it a little bit over the top when we say no functional, like very much reduced amount of B cells. Does that make sense? This is a juvenile diabetes. It's diagnosed usually pretty early. Okay, and it is it's treated. It's not cured, but it's treated by taking insulin, either via shots or via insulin pump. Pumps are more and more common, and I know there's a guy who actively works on developing a system that would deliver insulin automatically. So basically, you would have a probe in the bloodstream that will monitor your blood glucose levels. And when they rise, it will deliver just exact amount of insulin. So they will not go up and down, but will stay, around 100, how it's supposed to. That make sense? Clear? The type 2, that's my favorite type. Insulin resistance. So what is that? Did I tell you about the Temple of Diabetes before? So Temple of Diabetes exists in pretty much every American city, relatively large American city. And the name of the Temple of Diabetes is Cheesecake Factory. So if you go there and you ask for the cheesecake menu, do it. I don't know if they changed, but I've been there second time and last time, maybe 4 or 5 years ago. And I was glancing through the menu, and it was marvelous. So let's start with the fact that the slice, they start with 14 or 1500 calories per slice. Yeah, I know. That was my reaction, one slice of the cake. They're probably delicious. I don't know. I never tried, but they probably are. And I'm not a lazy type, so I went all the way to the end of the menu. And you know how sometimes in the restaurants they offer you extras, like you can have extra bacon on a burger, or extra cheese, or extra pickles. So in the cake, what can you expect? Probably, I don't know, extra raspberries or some extra chocolate, right? Some specifics. They have extra calories. You can add extra 400 calories to a cheesecake. That's it, just 400 calories. Whatever. I don't know how. I don't know what they infuse there. Huh? It's.
Just gonna ask, what are they?
I have no idea. Don't ask me. Ask Cheesecake Factory. But now think about this. The easiest way. Well, you can add fat, obviously, or sugar. But case in point, you consume an enormous amount of sugar in one sitting, right? So your blood sugar spikes, right? And you release a lot of insulin, Okay? And insulin tells your mostly muscle and liver cells to, get the glucose. And it does so through the receptor. Now, you double it down and you get another cake, and your glucose stays high, right? So more insulin is released, and it acts on the same receptors. And eventually, just like in a tale about the boy who cried wolf, receptors, due to the constant signaling, they become resistant. Does that make sense? So they require higher level of insulin to get activated. Pretty much the same way people who, for instance, use intravenous drugs like opioids, they eventually get used to a certain dose, and they need more to get the same effect. Does that make sense? So in a patient with type 1 diabetes, what you're going to see, no insulin and high glucose. Does that make sense? In a patient with type 2 diabetes, you're still going to have high glucose. And what do you think insulin levels are going to be in such a patient? They're going to be higher than normal. And it's kind of interesting that we still treat type 2 diabetes often with insulin. Does that make sense? So okay, let's double down on that. Let's just give them more insulin, which will just accelerate the development of more insulin-resistant phenotype. That makes sense? So the good news is that, well, first of all, there is some glucose uptake all the time without insulin. We know that exercise generally increases insulin-independent glucose uptake in the muscles. So for people with type 1, it means that if they exercise, they will need less insulin. That not completely wean off it, but less insulin. That makes sense? What is really cool, people with type 2 can basically change their lifestyle and be insulin independent if they do it early enough. Does that make sense? Now you may have heard, if you will look, I think I have maps in the notes, but if you will look at the maps of obesity in the United States and diabetes, they overlap. I can marvel about obesity for a really long time. I studied it for 5 years. One of my favorite topics. I don't know why I did that, because the solution is eat less. That's all. You don't need to study it in mice. And it's bad. Yeah, we know that. It's interesting though, the distribution. I call it an obesity belt. It's the southern states, starting in Texas. It goes all the way to Florida on the south and jumps in Tennessee. But interestingly enough, the two states that fight for the highest obesity rate are Louisiana and West Virginia. Okay? Obesity is the disease of the poor because of lack of proper food choices, lack of time to get the food, to cook it, a lot of stress. That all contributes to the development of obesity. Does that make sense? Now, when people tell you, oh, type 2 diabetes, these people, they aid themselves to this condition. Not exactly. So there is a certain level of genetic predisposition. Does that make sense? There are known cases of so-called benign metabolic syndrome or benign obesity, when people are obese, maybe even morbidly obese, but they do not have an abnormal glucose metabolism. They do not have type 2 diabetes. That is known. And on the other end of the spectrum is people like a friend of mine is 60-something. He's leaner than me. He exercises and he eats well, and the reason, he doesn't drink beer, he doesn't eat sweets, because he has type 2. He controls it. He doesn't take any insulin whatsoever. He controls it really, really well by the diet. But by looking at him, when he told me that, dude, you gotta be kidding me. He's not the type you would suspect type 2 diabetes in. So there is some genetic component. But you have to understand, on the bell curve, In the center, the biggest part, people who aid themselves to this. Does that make sense? So, questions? Yeah, you can check your glucose metabolism actually by yourself. You can do something that is called oral glucose tolerance test. I don't remember how much grams of glucose per kilogram of body weight, but basically you're making a really, really strong glucose solution, like really sweet solution, and you drink it, and you start taking your blood glucose using glucometer. Zero time point, 15 minutes, 30, 45, 60, 90 minutes, 120 minutes. That's a classic oral glucose, OGTT, oral glucose tolerance test. What you're going to see, you're going to see glucose going up and then going down. So it will be shaped, it's not for the exam, just FYI. It's going to be shaped like this. And if by 2 hours your glucose levels go back to normal, you're fine. Okay. If not, depending on the grade, and also it has to be fasting glucose, so you have to fast for 6 hours before that at least. And you can check it. That makes sense? Okay, to wrap up, know the difference between the types of diabetes, know the effects, know the mechanism that the one I killed about the insulin release. Any questions on this one? You clear? Awesome.